That's the second part we will be building. But first, let me check if the stream is up and running. Yep, looks that way. Okay, so last time when we stopped the previous stream, I was trying to add if statements to this language that we are trying to optimize using dead code elimination. But I was running into some problems, mostly with computing the successors of each instruction. And I also had to refactor some stuff, and yeah, I couldn't resist, and yeah, I started implementing it, and yeah, I have the solution now. So I will go over it and explain it, and I think then we will leave this experiment for now. I have some more ideas for it, but I need to think some more about it. And what I have planned then is to implement this blog post, which is like a really long introduction to Datalog, which is a logic programming language, and it's the blog post is in Python, and I want to write it in Haskell. So yeah, I foresee some problems with Python being dynamically typed and Haskell having types, so we will have to do more thinking up front, but I guess that's part of the challenge, and we'll see where we end up. But first things first, so yeah, compared to last time, what are the changes that I made? So first of all, I added some documentation in case this code will in case it collects some dust, and it will be some time before we revisit it again. So one of the things somebody mentioned last time, that this language I was at the end mixing up expressions and statements, and that was a good point. So I split it up into two parts. So we have the instruction, which is basically a statement. And we have only one kind of expression right now, and that's a variable. So you can look up a variable. And our language only has integers, so you can make an if that looks up a variable in the condition. And if it's non-zero, so it's like JavaScript or C, then it will go to the true branch, otherwise to the false branch. And the true and the false branch, they're both lists of instructions, so yeah, basically a block of code. And yeah, on the top level we also have a list of instructions, and that's a program. And yeah, that's an easy way to split up the expressions and statements. I think in a real language it would be a little more complicated, but let's keep it as simple as possible. So yeah, here we had the helper functions from last time. Yeah, nothing special about those, I guess. Yeah, also the mechanism for generating the unique IDs is the same as before. So we need the unique IDs so that we have an easy way to identify each of the nodes in our AST, so that we can use Datalog on it, and then at the end we can see which nodes of the AST are dead, and then we can filter them out. But yeah, in a real compiler, I think somewhere at the beginning, at the parser stage, or maybe right after it, I think that would be a good place to add the node IDs. So yeah, what I did is, instead of doing it at the parser stage, is I annotate my AST explicitly. So first the annotations are empty, it's unit. And at the end we will get back yeah, an instruction exactly the same, but the annotation is now an ID. So yeah, for each place where I had an empty annotation, I generate a fresh node ID, and then I rebuild the AST node basically. And if we have recursive parts, then we go deeper into the recursive bits, and then we annotate those as well. So that's, I think, also the same as last time. Then we have our Datalog algorithm that's built with Soufflé Haskell, a library of mine. Yeah, this is also the same like last time. So yeah, if you want to see more of the workings behind that, look at the previous part. Oh, I forgot I don't have chat open right now. That's silly. Hang on a minute. Yeah. But yeah, it uses the, yeah, I think the general data flow equations, and yeah, used in most languages, and they just work here as well, because our language looks a lot like those languages. And it's just really powerful how short it is in Datalog. It's like almost an exact translation of the formulas. So first we do liveness analysis of the variables to see where are each of the variables alive, and then we do dead code elimination based on that. So each line where a variable is defined but where it's not live, yeah, there is dead. So, and with this algorithm we can use Soufflé now to compute all the information. But in order to do that, we need to start up Soufflé. That's also the same as before. And what's now comes the part that's different. So I have two. There's two. I split up the fact gathering into two parts. So the first part is done by extract facts, which basically figures out if a variable is defined or used in a certain place. And yeah, that function is like nice and short, so let's keep it that way. And then I have an extra helper function now to compute the successors. And so I made like a snippet here with some C-like or JavaScript-like code, just to give you an idea of what the function does. So I annotated each of these lines with a node ID at the end. So, and if branches, they can hop either to the true clause, or they can hop to the else clause. And yeah, you can have nested ifs. So for example, this print y, that eventually ends up all the way at the end, and also this print y ends up here, and also this print 42 ends up here. So yeah, it becomes quite complicated. So also the function is quite complicated right now. I think it can be done much simpler, but for now, for the experiment, I'm just keeping it this way. Maybe later I will refactor it using recursion schemes or something similar, probably. But basically what it does is, for each of the instructions, first I compute all the next IDs, which drops the first of the instructions, and then maps the getID function over it. And if you have that, then you can do zipwith, and then another helper function g, and that helper function now gets the instruction as well as the next ID of the instruction next in line in a really handy way. So yeah, what you need to do now is you need to compute the last IDs of the current instructions. So for an if, that's the last instruction of the true clause and last instruction of the false clause, if you have it. For each of those, you want to say that you jump from those instructions to the next instruction. So I call those the direct successors, but you also have nested ones. And for the nested ones, that's mostly with an if now, but if you have other control flow constructs, yeah, this function would become bigger. But in the true and false, if you have a if AST node, you have to go into true and false branches, and for each of those you have to compute the successors again. So yeah, we are lucky here that they have the same form as a top level program. So we can use recursion here, and yeah, that computes all the successors in those branches. And then what we also need to do is we need to compute the first instructions of the if in the branches, because after evaluating the condition, you jump into one of those two branches, so you have to mark those as successors as well, and then you concatenate everything together, and then it's then the algorithm is finally over. So yeah, this is a really big function, but yeah, I think I should refactor it in the future somewhere. So I was explaining here with the that code elimination function. So we use both of these helper functions that I just explained to get all the facts, and we add them to Souffle. Then we can tell Souffle to run it, and then we can get all the results back. And if we have the results, then we can call the simplify function. And simplify is defined here. So yeah, for each of the that code facts that we get back, we extract the line numbers, and for each of those, yeah, then you map over the instructions, and then you check if the node ID of the instruction is in the set of line numbers that are marked as that code. And if that's the case, then you should then it should be removed. And yeah, that's done with map maybe. If you return nothing, it gets deleted. And otherwise, yeah, then we know that we have to keep the instruction. But if you have a nested instruction, then you have to recurse there as well. So that's why I have the transform function. And again, if you come across an if, then it has to call the that code elimination on each of the sub branches. For normal instruction, it's done. So that's all you need to do to simplify the program. And then we had the helper function to get the node ID. That's not that interesting. Yeah, the evaluator or evaluation function is also not that interesting. I think it's the same as before, but I added a case for the if. So what we do is we look up the condition, which is basically always a variable right now, which is why we can do this directly. Yeah, if we don't find it, then we have an unbound variable, and that's bad. And I just printed out and I tried to continue. But yeah, the real program would probably exit there. And if we do find the variable, then yeah, we do the actual check. If the value is not equal to 0, then we go in the true case, and otherwise in the false case, which is the behavior I said before. Then we had a lot of test scenarios, and I added some extra ones containing ifs. And I should probably run the code to show that everything works. Oop, syntax highlighting is a little bit strange. Okay. Wow, that's a lot of scenarios. Let me see. So, hang on a minute. So the first scenario here on the right, there's no dead code in here except for the assign x equals to 2. That's dead code because we have an assign x is equal to 3. And it deletes it because here we only have the assignment of the value 3 to x. So it works in a simple non-nested if, so the branches also get optimized. And like the next scenario, I think that's the same. That's a duplicate scenario, I think. But yeah, let's leave it here. And let me go to the next one then. So let me see here. Okay, so this one says this x should be deleted because it's either deleted here or here. And this one should also be deleted because it's assigned here. And here I had, it's not smart enough yet to delete this one. don't know why, but it did delete the one in the if in the true branch, and I think, but I'm not sure. Yeah, I think this is a limitation of how I built the algorithm, but it might be because of a bug. That's something I would have to look into. That it doesn't see that it's always assigned. Anyway, the next one is special because we have nested ifs now, and this one should be deleted. So that is this case, I think. Yeah, because the assign of 2 to x is deleted, and we only have the assignment of 3 to x. And the rest is fine. And then the next scenario, let's see. Okay, so we assign x after the if, so both of these assignments are pointless, so they should be deleted. And then we end up with this here. So yeah, the if has 2 empty branches, so both the true branch and the false branch. Yeah, I didn't build anything to delete empty ifs, but yeah, that could be done maybe in a separate pass or in this pass. That's completely up to you. And what's the final one? Yeah, the final one shouldn't delete anything because we have a print here and then an assignment. So yeah, there's no dead code at all in here. So yeah, that's it. And yeah, at the end I had the code to run the program. But yeah, that was the dead code elimination. So I learned a lot from this. And okay, I have to admit, once I added if statements, it became a lot more complicated. But still, if you look at the algorithm, it's super short. So I don't think this is an algorithm I would have been able to write myself in another language, but in Datalog it's just really short and succinct. So yeah, that I think this is a good showcase of the power. And because of that, I also think it's a good idea to just experiment with Datalog and build our own engine. It will probably be super slow, but yeah, it's all about learning, right? Okay, so by the way, I pushed all of this on GitHub. Oh, that's for in a minute. So yeah, on my playground branch, this is where I stored that code elimination, and it's in a different branch, like the README said. Yeah, if you are interested in the code, it's all there. So what I'm gonna do now is create a new branch, start branching off from master, and then we will start porting over the Datalog engine. Okay, so yeah, just making sure what the state of the project is on master. So let's open terminal. Okay, add some syntax highlighting. We might do like a horizontal split, because then I can have the web page and Vim open at the same time. So let's go to main. Not sure if we need souffle Haskell this time. Maybe if we go really fancy, but not right now. Okay, so let's do the horizontal split, then like this. Okay, now it begins. Warning. First of all, I have the tendency to want to skip over blog posts that are really long, and this is one of those. But this time we have to go really slowly and port over everything that we come across. Let me do it like this. So it starts off with simple facts. So yeah, in Datalog we have facts and relations. So maybe I should open the Wikipedia page first. So facts are like this. They're just saying, oh boy. This is saying that Xerxes is a parent of Brooke and Brooke is a parent of Damocles. So yeah, and you can encode it any way you want, but a fact is just you have like some kind of relation, and then you have the arguments, and that's the relation combined with the arguments is a fact, and it's always ended with period. That's one thing. And if you have a lot of facts, then you can also build relationships on top of those, and then it can look like this. So, and this is saying, so this is like a rule that's saying X is an ancestor of Y if X is a parent of Y, or so yeah, we have two rules here, so you can read that as an or, and X is also an ancestor of Y if X is a parent of Z and Z itself is a ancestor of Y. Phew, that's already quite something. Supi, sorry, I just read your comment, but yes, the most difficult part was for me was the computation of the successor. So maybe I need a different data format to make that easier to compute, or maybe something like a recursion scheme to make it easier. I need to figure that out, but yeah, it is much simpler now. It's just pure Haskell code, and I think the problem is a lot smaller than before. So yeah, I think that's the win here. Sorry that I didn't see the question earlier. I was too busy explaining all the time. Where was I? So I explained facts and rules. And this blog post starts with facts. So okay. I should make it so that I have notifications if people say something. Then I get like a sound, and then I know what to that I need to react. Anyway, so the blog post starts with facts, and here they mention rules. So, and here the Python code starts. So we can't do those imports, so we skip that. And now we need a type for variables. So let's make that. And let's make it a new type. We can always make it a type synonym later. I don't think it really matters that much right now. Let's add show. Not sure if we need EQ. So now we can make a variable X. It's like super simple, but let's go over it step by step. And it's complaining that it's not used, but that's completely fine for now. So the next part is about relations. Okay, so I think a relation is more like a fact on the Wikipedia page. So what is going on here is they are building a data class again, like with variable. Oh, I might have went over that a little too fast, but so it's a data class, so just a collection of data basically. And fact has a name and some attributes, and the attributes are a tuple. Okay. Let's delete this for now. So we have a fact, and a fact has a name. I guess we can make it a type synonym for easier reading. We can always refactor it later. And I think what we need to do is, if we want to support facts with a different kind of amount of arguments, I think we just need to use a list instead of a tuple. And Python can get away with it because it's dynamically typed, but in Haskell, you have to, you can't mix and match tuples of a different size. So, and the tuple has to be of a certain type, so I think we can call that term. I don't know, I think the correct word for this term, so the Wikipedia page also has a syntax for Datalog. And here we have a fact, which is a relation. Is that defined in here? I think that's just the name of it. And then the constant list. The constant list is one or more constants. And yeah, then you also have a term here, which is a constant or a variable. So yeah, I think here, I think term is a correct word here because it also uses term for this. Yeah, I think it's best if we stick to the the blog post. That's difficult enough already. Let's see. So yeah, we did this part. And now it's talking about rules. So we have facts, but we need to add rules. So you can have a rule of, with one clause, I guess, or what is it called? No. An atom. Okay, so that's called an atom. So you can have one atom or you can have multiple ones. So you have the head part and you have the body. Okay, so the body is a set and the head is a single relation. Oh, and a relation is like what we call a fact. So the mapping might become a little bit difficult, but let's make a rule. Let's also add some new lines. So we have a rule, and there we have a fact, and then a list, or a set of facts. Let's use a list for now to keep it easy. Okay, now we need a query, because with the facts and rules, with those we can build our database, and then we want to query the database. So it starts off with a query with just facts. Okay. Okay, so this is just saying what it needs to be able to do. And here it's writing some code. So let's also port over that code. So x is var x. 8 is a relation is then a fact. Okay, and now it will complain already. because it doesn't know that term. Yeah, so let's make a constant here. Oh, and we have to say that this is constant, so let's yeah, let's, okay, it might become a little bit verbose, but oh, interesting. Maybe I should also take a look at that blog post if we get stuck on this one. I think it's this one. Oh, it's even in Haskell. Okay. Yeah. I think that's cheating for now. So yeah, let's continue with this. It should compile, and it does. Yeah, it's giving us a lot of unused top binds, but that will change in a minute. So let's add Bob. Capital letter. And Abby. Oh, Abby is not a man. And now we need to make a database. So Abe, Bob, Abby. And what is the no rules? Okay. And then now what we need to do is build a query of a fact. And then, oh, here we have to say that it's a variable. Okay. So what I'm thinking that we should do is do it like this, and then variable, and then get rid of this. Oh, and now this will complain. Yeah. And now here we can say var x. Oh, maybe we should do it like this. Well, it doesn't really make a difference, I guess, but okay. And what he does now is he makes a function run simplest, takes a database and a list of rules, and then a query, which is basically a fact. Well, it's not really a fact, but and it gives us back a list of results. Okay, it will complain for multiple reasons now. So let's make these types. So what is a database? Database is a list of facts, I guess. Now we need a query. A query is a fact, I guess. And a result is also a fact. Okay, maybe just do this then. Okay, let's see where we end up. So the simplest run would iterate through all the facts and filter those facts that match the query by relation name. Okay. So, okay, what is going on here? So it starts here, it does filter facts on the database, the query, and it gives it the name match function, which is basically saying that the fact name has to be the query name. And then here in the filter facts, it does like a comprehension over the database, and it returns everything that matches. Okay, well, okay. So here we get our DB. We don't do anything with the rules now. Then we get the query. Okay. And now we need to filter on the database. Okay. So, and let's make this a record. Really can't type today. And fact terms. Still happy with that. So now we filter on the fact name of fact is the fact name of query. Okay. Yeah, let's make it a little bit shorter. So like this. It will probably be deleted further on in the blog. So I read a little past this, but yeah, it has a lot of example code, and it throws away quite a bit as well. So yeah, that's this entire block of code is now this this one-liner. Okay. So now it's saying let's run it. So yeah, let's do that. So let's results is run simplest database, and then the rules, and then the query. Okay, and then print results. Oh, now it wants to add show here as well. Whoops. Okay, it's saying that rules are not used. That's a little bit annoying. Can we turn off those warnings? I think it's like this. Don't know what's going on with my indentation. Oh. How do I do that again? Ah, I always get it the wrong way. There we go. 36. So let's call this one database then. And then okay. So it seems like it worked. So we have a database of 2 men and 1 woman, and the query is looking for man, and we get back at the bottom 2 men. So so far so good. Okay, so let's continue. Facts of length 2. So okay, now it starts also with the parent stuff. So Abe is a parent of Bob, and so on and so on. And now he wants to query who are the parents of Carl. Should return Bob and Beatrice. Okay. Okay, so let's build this part. And oh, that's clever to use a helper function to make it a little easier. Not sure yet what we should do with all this code here, but let's just leave it there. Let's move these types up a little bit. So let's see, we have to be able to make a parent. So let's see, facts. Well, yeah, we will probably get rules as well, and then the query is a query. Let's add some type annotations, makes it a little bit easier. This is a database, and then ape, Bob, Abby are all facts, and x is a term. Yeah. Okay. So let's So apparently it throws away all those facts. Okay, yeah, that's fine as well. What we can, so we can do just this, and then, so a parent is fact parent, and then parent, oh, yikes. Yeah, thank you. So this is a little bit like name shadowing already. Yeah. So a parent, so here it has two strings of a parent and a child, and then you get back a fact. So here we have a parent and a child, and then like this. What is going on? Oh, yeah, well, we can make these constants, or we can even do this. There we go. So now we have a function to create parents easily. Oh. And now we can say parent ape Bob, parent Abby Bob, parents Bob Carl. Okay, still happy with that. Yeah, as you can see, our query returns nothing now. It's printing out nothing. And now yeah, this part, the run simplest, that part needs to be upgraded, because if a query has to match, then an argument at a certain position needs to match the query argument at a certain position. So A needs to match X and Bob needs to match Bob. Okay, and we have to take into account variables now. Okay. So let's first build this the way he has it. So again, it's called run with filter now. So maybe let's comment this one out. Run with filter. Oh, now he's adding type annotations. Yeah, and we had them right. So run with filter. And again, he does filter over the database. He doesn't do anything yet with rules. So, okay. Matches fact. Well, we have Q in scope, so we can do this. Matches. Or just call it matches. And then here we get the fact. Okay. And now we are saying if fact name fact is not equal to the fact name of the query, then false, else. And what does he do now? So now they do a zip over the attributes. Okay. Let's first write it out and then figure out a better name. So zip of fact turns query and fact turns fact in. Okay, and now he loops over it, so we can probably do that all at once. That wasn't that notification startled me. Let's see, what is he saying here? If the query attribute is not a variable, okay, so it is a constant and it's not the same, then false, otherwise true. Okay, let's make a helper function for that. Query term fact term. Let's start up Google. Which one do we need? Do we need all or any? If all of them satisfy the predicate. So I think if they all match, then it matches as a whole. Okay. So let's not do a let here. Let's do all. Okay. Then matches olive. The query attributes and then the fact attributes. And now, wait, we just have to say that they're equal. So like this. Oh, and now it's complaining here. And I know we can refactor that a lot. Give me a minute. Oh, now we need equality. Oh, and we need to say if it's, but now it's different. So okay. So here, if it's not a variable, so if it's a constant then? If it's a wait a minute. Okay, I think that's it. That might make it a little more complicated in a second, but let's go with it. Oh, and now it has these things. Yeah, I think we have to refactor it out. Because fact, bool. Oh, hang on. Where? Now we do have to do this. Okay, now it's happy again. Because now we can do those assertions. So, matches, and then parent a Bob, and then parent, oh, I really can't type today. Now it will complain. First this. Yeah, it's complaining about X now, so that's a little bit unfortunate. But we can fix that. What we need to do is say that Abe is oh, so these are no longer strings, those are terms. Then we don't do this, and yeah, either we do constants here, but I'm thinking that maybe we should do this. Abe, then Abe is like this, and then Bob is constant. Bob yeah, and now you see that the type system, yeah, because it's so fast and loose, they can do that, but in Haskell it's a little bit more ceremony. Bob, Carl. Oh, and Beatrice. Line 80. Okay, so this is Bob, and this is also Bob. But this A is new now. So let's put Abby here to make it what is going on? So this is always true. No, still nothing. What am I doing wrong? So we do the zip. Oh, no. First the query, then the fact. So that's this line. If the fact name is not equal, then false, that's this part. And then here it's saying, so if it's a constant, so that's what I have here, of the query attribute. And if it's not equal, okay, let's wait, hang on a minute. I think this is the part where I made the mistake. So it's not equal, then false, otherwise still false. Okay, I'm doing something wrong here. Yeah, you also did that. Yeah, I still need to watch the first part of your stream, but the second part was fun to watch. What am I doing wrong? So here I'm saying does. Oh, it's flipped around, I think. Yeah, because I have the query and then the fact, and on this side he has the fact and then the query. So yeah, I was also thinking that while writing it, the order matters. Now it's true. Okay, progress. And this is absolutely hideous, and we will refactor that in a second. Yeah, don't mention it. If the stream is good, then it should be, yeah, you should be able to say it. Okay, so now he is moving X to there. And now it's failing again. Why? Oh, let's also make a third case. So here they put X at the beginning again, and here you have Abby and then Carl, maybe. Well, at least that's false, so 2 out of 3. But why is this broken? So doesn't help that we have it flipped around. So, oh, silly me. Yeah. Okay, it works. So true, true, false. But let's refactor this. So if this is equal, this is what I had. Oh, that's a little too much. This. True, true, false. So this is already a little shorter. So yeah, what I want to do here is this can be done a lot easier, because if you know it's a constant, then you can just do equality, and otherwise it's always okay. So if we filter, yeah, so the variables are always okay, so we are only interested in the constants. So is constant what am I doing wrong? Oh, yeah, I need to do first. So true, true, false. And now what we can do is we can say, now we only take a look at the constants, and now we can say that they all have to be equal. So then we can do this. Now it says that this is not used, and that's fine. And we still have true, true, false. And let's make it a little prettier. So or try to make it prettier. So like this. Whoop. And then is that easier to read? Think so. It makes me wonder if you can do a zip with a filter at the same time. No. Okay, let's avoid this. Go back to here. So we did this part, and it's a little simpler. Still not sure on this part. So if the fact names are not equal, then false. So can't we say that they have to be equal and then also that? Names match. And that's basically this part. I'm probably refactoring too much and it will be thrown out in a second anyway, but I want to have it readable. And maybe I should also start doing some commits. Let's see the time. Oh, we still have plenty of time. So what this is saying is it matches if the names match and if this whole thing matches. Ooh. Names match and attributes match. And then true, true, false. I think that's a little nicer, and I think we can go even further. So do equality on fact name. Oh, let's see. I think here query. Is that easier to read? Don't think so. Don't think so. Yeah, me as well. I sometimes program Elixir during my day job, and there we have an operator like this, and it's basically this operator, and sometimes it's yeah, I find it easier to read. But yeah, you might as well say then that this is flipped around as well. Oh, whoa, what am I doing wrong? Did I make a mistake? Okay, that's strange. Yeah, it goes a little too far, but not sure on this one. I think I'm gonna revert this. Yeah, Elm as well. Yeah. So here I'm gonna say this. So Q. Let's not over-engineer it. So yeah, this version is maybe a little bit more verbose than the Python one, but yeah, you're right. Let's do that. So first, yeah, probably can't find it. So import. I think it's this one. Yeah. Yeah. Let's see, where was I? So run the filter basically says filter over the database and everything that matches the query, that's what we want. So that's actually a really nice translation. The matches function, it takes a query and the fact, and the names have to match and the attributes have to match. And names matching is based on the fact name, and attributes matching has to, yeah, takes a look at the terms, and then it filters out all the constants, and then all the constants have to be equal. Yeah. Oh, the precedence is bad. Yeah, I think it's fine for this case, so let's leave it here. I'm gonna make a commit for this. Let's make a new terminal. Oh, and let's first do this part and then add it. So what do we do? Okay. Run the filter database rules, and then the query is this. So the query will change. Maybe we should move the query a little bit down. So the query is parent, and then X, and then Carl. So it's saying Bob and Carl, that's this one, and Beatrice and Carl. That seems to work. And then we need like another results, or well, yeah, let's add results prime, and then query prime. Oh, and here we can even say parent X Carl, and here we can say parent Bob X. So yeah, now you have to watch out and only read the last two. So Bob and Carl and Bob and Connor. Yep, it works. Yeah, the precedence thing, it's not that straightforward. It's yeah, there's so many operators in Haskell. Yeah, if somebody attempts that, yeah, that's not going to make anybody happy because yeah, they always want different precedences. So I try to just get by with what I have. I'm more than happy enough that I can add my own custom operators. That's not possible in most languages. But yeah, precedence is yeah. So everybody wants something different. Yeah, how should we name this? Follow block up to run with filter. Okay, let's continue. So I think that was everything related to facts, and now we are going to do rules. So a human, yeah, some human X is a human if it's a man. So and the example has 2 men and 1 animal, so it should return this. Okay. So okay, so it's making helper functions again. Does that mean that we can remove the previous stuff? I think so. Yeah, it's building a new database and it's adding a rule now. Okay, so this can all be deleted. So man is, it takes, yeah, a term, I guess, and it gives us back a fact. And animal as well. And human also. So man is fact. Man. Oh. Really can't type today. Oh. Oh, now it's complaining about all these. So okay, that's better. Okay. Oh, and now it's complaining about shadowing. Yeah. There we go. Let's see. So we have our 3 helper functions. We have the variable x. Now we need to make the head. So head is human x. Body is man x. Oh. What is going on here? Oh, yeah. So here we have to say constant. Oh no. Here we have to use this x. Yeah, that's good. Yeah, it's tripping me up because here the lowercase x is a capital here, but that's not possible in Haskell, but then I have to remember this part here. Anyway, we have the head and the body now, so now we can make the rule. Like this, okay. So here goes the head. Oh, let's call this head prime. And then the body goes here. Okay, that seems to work. Maybe we should define it like this. Still happy. And then, oh. Okay, like that. Now we can make a database. Man constant. Oh, darn it. Should have kept ape and the rest. So ape, Bob, terms. So ape is constant ape. Bob is constant Bob. And oh, we also have a tiger. Tiger. Man Bob. Oh. Ape. Man Bob. Animal. Tiger. Yeah, it's probably crashing somewhere down the line. That's fine. Because the query is undefined. Yeah. So the rules, so now we actually have rules. So the human rule goes in, and the query is human x. Okay, nothing is being returned. That's because in the next part he makes the matching part smarter. Okay, this is quite a block of code. Okay. What is going on here? So for each rule, for each relation in its body, if it matches with any of the facts in the database, then get the attributes of that fact and create a derived relation with those attributes. So if we have man and we know our rule is this one, we add a derived relation to our database human. Okay. So what is going on here? So let's start at the bottom. For now, our body has only one relation. Okay, so it takes the first one. And then it calls this helper function. It finds all the matches. And what then? For attributes in all matches. Okay, it's starting to look like he's running into a lot of Python specific things. So he has like a helper function to evaluate a simple rule, but okay, so the example continues. It's basically all this code all the way from here to here. So that's actually quite a bit already. So this is purely about the rule matching. And this part is if the rule matches the fact in the name, then it goes over the attributes like before. But it returns it. Okay, so I think that dictionary can be thought of like a unification kind of thing. So if you find variable on one side, then it will be something else on the other side. And two constants should be the same. And then it does that here. So what is going on here? So if you have the attributes, then it appends it. So you get, it does that for all attributes, so you get a list of lists, I guess. Wow, how can people program in this? And then here it does rule.head.name. And here it's building up facts again. Okay, so what this entire part is doing is just thinking which facts are new. And it does this by matching the relation everywhere in the database. If the facts don't match, then it stops. Otherwise, it returns a dictionary that is used here. And then it's appended, and then here it builds up all the facts again. But I think that can be done much simpler. But yeah, that's my claim. Evaluate rule simple. So a rule goes in, then a database, and we get facts back out. Okay. So what is it doing? It takes the first clause or atom was the thing. Let atom is, and then rule body. We need to make that, and then we do the head on that, and that's unsafe, but I know. In undefined. Okay, now we need to make rule body. Let's make this a record as well. Okay. So we have our atom, the first one. And it's saying now, so what it wants to do is what does this do? Let me open up a Python shell. Python 3. So A, 1, 2, 3, 4, B, ABC dot values. Okay, so it's like object values in JavaScript. Gets only the values out of the dictionary. And then it makes a tuple with that. So then you get the tuple 1, 2, 3, 4 ABC. Okay. Wow. Let's see. So let's rebuild part of this, I guess. It's becoming complicated. So he goes over the database. Matching facts is filter, and then db. Oh, and let's make this a function. So name matches f1, f2. Here you get f1, f2. to view facts, and then here name matches facts bool. It's still complaining, so name matches wait a minute. Of the fact name of the first atom. So here you have a fact, so that's first atom, I guess. Oh. Okay, so like this. So everything that matches the name of first atom, we filter that. So then we get all the matching facts. So then we get this, but I need to watch out here because what is he doing? All matches, so for each fact in the database, he does match relation and fact. Okay. But oh, and the fact well, I think this is it already. It's just I think he is making it too simple right now, like just this part, and maybe he adds more later. Let me see. Oh boy. No. It's strange. I would expect here that it's is it because the rules don't have any constants in them yet, that it's just adding them automatically? That's strange, but okay, let's do it like this. Yeah, okay. I'm liking how this entire block of code, okay, there's a comment in there, but it's basically 3 lines, maybe 2 lines. This evaluate rule simple can be passed to a function which will evaluate it on each rule for database to generate the final knowledge base. Okay. Oh, nice, some mutable stuff here. Okay, that's easy. So generate knowledge base, and then you give it list of rules, and then you get database. space. Okay. So for each of the rules, so that's a map, but you get back extra facts. So that's a concat map of the rules. And here you say, I think we should flip it around, then it becomes easier. Then concat map evaluate rule simple db. Okay, it's happy again. So we have our knowledge base, and then, well, one thing this does is, yeah, because it's working with sets, yeah, I think, isn't that a function called nub? Yeah, but it's on squared. So yeah, anyway, let's add it. Oh. Boom. So we have our generate knowledge base function. And finally, we have run rule simple. So now he generates the knowledge base, and then filter facts, query variable match. Did he build that before? Because then we can reuse it. Ah, yeah, we have it. So that's, I guess, this one, matches. Okay, so we're really close now. So we can make run rule simple. Then this becomes also run rule simple. Still happy. Oh. Generate knowledge base. Oh. Okay. I think we did one different thing, but we can fix that. So we have our knowledge base, and now we use that instead of KB. So first we compute derived facts. Nub ord. Is it faster? Let me see. The formatting is messed up, but ON log D. Think that sounds better. Which thing is it? Containers dot list utils. Okay. Oh wow, we're actually using the rules now. Oh, we need to make fact an instance of port and term as well. Oh, this might become a little strange. let's go with it. The run simplest, that can be deleted. What he did here is he has like this, he passes in the function here. So f, and then f is database goes in, and then a rule, and then you get back facts. And then here you get f. Did I make a mistake? Oh yeah, of course, this becomes evaluate rule simple. Now it's the same. Oh, thanks for the optimization then. Okay, so it's saying now if you run rule simple, then you should get stuff back, and we don't. Why? Why is it not working? So we have our query, which is saying it should be a human. We have our database. And we have our human facts here, and then we have a human is a man is a human. That looks right. So let's put a rule on it, type signature on it. And then we add 2 mans and 1 tiger. Where is it going wrong? Yeah, the rule is in here. Let me see if the warning isn't hiding anything. No, that's fine. Let's go over it step by step again. So here he is saying generate knowledge base, evaluate rule simple, database and the rules go in. And then he filters the knowledge base with the query, and then query variable match. Query variable match should be this one, and we have that working. Okay, so the problem is probably generate knowledge base. So for each of the rules it says generate me all the facts based on the database, and concatenate it all together, get rid of the duplicates. Yeah, that also looks fine. And then here we have evaluate rules simple, and that is saying this part. So we get our first yeah, we get the first atom out of the rule body, and then what it's doing here is match relation and database. So it goes over all the facts, and if it matches, then it's a matching fact. So, And when does it match? If the names are the same. Hmm. I think I figured it out, because what we're doing here is we are returning the facts, but it's only interested in the attributes, and then here it's putting a different name on it. Oh boy. So these are the matching facts, okay? And then map. And what do we map on it? So first, yeah, we need to do two things. We need to get the fact terms out. So fact terms, if we have that, then we can hang on a minute. What does a rule look like? So we want the rule head and then the fact name of that. So, okay. Rule name is, so the rule head of the rule and then the fact name of this. And now we can build a new fact with the rule name and then the fact terms. What am I doing wrong? Oh, right. So I need to do this. And it works. Okay. It's nasty because this part is hidden here and that part, yeah, it's all over the place. Yeah. So what's going on now is for each of the matching facts, we create new facts, and the fact is of the rule name, but with the fact terms of the matching fact. So infer fact, then terms is, and then or do it like this. Makes it a little more explicit, I think. Yeah. Phew, that was a difficult piece of code. And what should it say? Abe and Bob. So, Abe and Bob. Okay, that works. So, let's commit it. Add evaluation of rules. Okay, it's quite far already. I have 15 minutes or so, so let's see how hard this is. Oh boy, that's quite a bit. But it's probably a lot of setup code, I hope. So it will, now we need to do logical AND, which is, it will solve this issue. Fix me. So let's go back to our database. Oh, and it's adding all those things back again. Okay. Man, woman. And parent we need also again. Oh. Okay. Okay, and there's also a father rule. So something is a father if it's a man and if it's a parent of somebody else. Okay, so we need to add a new variable apparently. Done. We did the woman part, but we need to add father. So I guess that's similar to, yeah. A and B, I guess, is fact father A, B. And then our database, oh boy, Abe and Bob. We don't have it. That's funny. I just noticed that not everybody from the people is in the fact list. So what are they? Not men? They're not women? Are they aliens? Yeah, let's just keep it exactly the way they have it. So yeah, it will probably complain all over the place. Yep. Abby, Carl, Connor. Anomalies, yes. Yeah, if it was JavaScript, it would probably be undefined. Let's see, so I added Carl, I need to add Connor. Oh, getting to add the women. And is that it? That's it. Okay, so we have our database again, but we need to add the rules. So only the father rule now. So I guess this one can be deleted. So the head is father XY and the body is parent XY man X. Oh. Okay. We are getting no outputs. Yeah, that's probably because the logic is not smart enough yet. Yeah, we need to add logic for the conjunction. So, okay, so yeah. So what it's saying is, because we have the variable x at 2 places, now we need to make sure that x is the same in all the places. Yes, they are. So, but yeah, I'm just following the examples. So yeah, if you have x or another variable in multiple places, it always has to match. And what's this here? And this doesn't match because there's no man Abby, because there's no man, or yeah, x is never Abby. Okay, so this has common value. Okay, so I think that has to do with unification kind of thing. We also have to start pairing variables to values. Yeah, that's probably, yeah, it's starting to become more functional. So they take a look at all the keys, they take the intersection, so those variables are the same, and then you get like this is like a set of variables, and then for each of those variables it looks in the list and checks if they are the same. Yeah, that's actually quite a easy to read function. So yeah, let's make that. Where to put it? Here. Okay. It puts an any there. That's not nice. So x can be a term, I guess, or the any can be a term. So what we get is a map of variables to terms, and then another map of those, and then a boolean. There's a lot of boolean blindness. Whoops. As map and import data.map map. Oh, it's called a variable. Okay. Others 1, others 2. Okay. To Google. Map keys. Hoople, what's that about? Let's go to data.map, and then keys. Oh. Difference with key, but I want to do for the keys existing in both maps. So I need map.intersection. Jesus, let's call it M1, M2. Well, okay, let's map intersection, others 1, others 2. And here we have to do something to get the keys out. So size lookup. Come on. Is there no way to get the keys out? Map keys, no. Folds. Oh, just keys. Did we do it right? So common vars is list of variables. That's what we want. Nope, this one. So we have that, and what now? Oh, now we need to do an all. And then, okay, so we need to do like a zip on, no. So for common vars, for each of those, we need to do a function dot lookup v is others 1 is lookup v others 2. Did I do something wrong? Oh. It's incredibly hideous. Key set. Oh, is that better? Keys set. Okay. Well, that works as well, but I think all, does it work with any foldable? Yeah. Lucky you. Key set. Yeah, that works. Thanks. Yeah, this, I want to make a helper function for that. I feel like I can say this more easily, like, so we want to do map.lookup v on both. Let's see. We can put this. I think that reads a little bit easier. So we get all the common variables, and then we check if all of them have matching attributes, and we do that, and that's doing a lookup on both and checking if they're the same. So that's this part. Once we have that, we know that match relation and database will return as before a list of body attributes with which each match a fact in the database. Okay, so it's saying that you can get facts for this and then facts for that. And Whoa. Okay, and I'm also taking a look at the time. Yeah, I'm thinking that we stop it here for today, and yeah, that we just continue where we left off last time. So is there an easy way, like an anchor tag kind of thing? Oh, that's wrong key binding. There we go. Okay, well, that's it for this time. So, yeah, you're welcome. Well, I think at one point I will get it working, but the performance will probably be really bad. And then, well, I hopefully will get some kind of feeling into how this works. And then I want to take a look at how I can make it fast. But that's probably going to be much more complicated. So, yeah, thank you guys for coming. Well, I'm used to Soufflé and it's super optimized, and I think this is like a really straightforward approach. Yeah, and exactly. If you build a few prototypes, then you get the feeling, and then you can iterate on that and build better and better stuff. But yeah, in the end, I want to do like the kind of tricks that Soufflé does. So if you're interested, then you can take a look at Soufflé. But it does all kinds of crazy things to speed up the performance. And it will probably involve writing a complete compiler. Yeah, but I want C-like speed and not Haskell speed. So yeah, it can be made much faster. Anyway, I'm gonna quit it here for today, and I will continue next Sunday with this. And thank you all for coming. Yeah, exactly. The algorithms matter more than the language. But yeah, I'm gonna end it here, you guys. So thank you all, and hopefully see you next week. Bye.